Are there different types of quantum error correction codes? Have you ever wondered how quantum computers manage to keep information intact despite the challenges of noise and interference? The answer lies in quantum error correction codes. Yes, there are several different types of quantum error correction codes, each tailored to protect quantum information from errors. These codes are essential because quantum information is delicate and can easily be disrupted. Errors in quantum systems typically fall into two categories: bit flips and phase flips. A bit flip occurs when a quantum bit, or qubit, changes from 0 to 1 or vice versa. Phase flips affect the relative phase of quantum states. To effectively preserve quantum information, error correction codes must address both types of errors. Let's look at some key types of quantum error correction codes. The repetition code is the simplest one. It works by encoding a single qubit into multiple qubits by repeating it several times. While it can correct bit flip errors, it does not handle phase flip errors. This code serves as a basic starting point for understanding error correction. Next, we have the Shor code, developed by Peter Shor. This was the first quantum error correction code and encodes one logical qubit into 9 physical qubits. It can correct any single qubit error, including both bit flips and phase flips. However, it requires a significant number of qubits, making it resource-intensive. The Steane code is another important type. This 7-qubit code can correct both bit flip and phase flip errors. It is designed to be fault-tolerant, meaning the error correction process itself does not introduce new errors. This code is more efficient than the Shor code and is widely studied for practical applications in quantum computing. Then we have the surface code, which is a topological code that arranges qubits on a two-dimensional lattice. This code has a high error threshold, allowing it to tolerate relatively high error rates before failing. Surface codes are promising for scalable quantum computing and are used in many current quantum architectures. Another interesting type is the Bacon-Shor code. This subsystem code separates error correction into smaller parts, providing good error correcting properties with potentially lower overhead than some other codes. The Hastings-Haw code is designed for specific hardware, such as Majorana qubits. It offers better spacetime efficiency in certain situations, but may be less efficient for gate-based quantum computers compared to surface codes. Additionally, there are three-dimensional color codes and other topological codes. These codes generalize surface codes into 3 dimensions or other topological structures, offering improved error correction properties and fault tolerance. Lastly, we have bosonic codes. These codes encode quantum information into modes of harmonic oscillators rather than discrete qubits, providing hardware-efficient error correction for certain quantum devices. In summary, quantum error correction codes come in various forms, each with trade-offs between complexity and error-correcting power. The choice of code depends on the specific quantum hardware and the scale of computation. Surface codes, currently representing one of the most practical approaches for large-scale quantum computing, while other codes like Shor and Steane codes provide foundational concepts for specific applications.